because this format is really keep you on track. So go ahead.
Okay, so I'll wait for the first slide, but in this first presentation I'm going to be talking about engineering at the smallest length scales, which is the nanometer scale regime. A nanometer is 1,000th millionth of a meter, so we're talking about engineering innovations at close to the length scales of molecules or atoms. Now, there are four major platforms which have enabled this revolution in nanoscale engineering. The first is the ability to discover entirely new materials at these very small length scales. So materials such as carbon fullerenes, carbon nanotubes, shown on the bottom right is work from RPI, studying the properties of single atomic layer thick sheets of carbon called graphene, which have extraordinary electrical, thermal, and magnetic properties. The second key platform is the ability to engineer and manipulate at the atomic and nanoscale. So the top images show Don Eigler's work from IBM, moving individual atoms around on a surface, and then the other images show work at RPI in assembling polymer nanocomposites and molecular glues. The third platform is the ability to measure and image at these tremendously small length scales. So the ability to image individual electrons and individual atoms on surfaces using scanning tunneling microscopy, using the electron microscope. In the bottom right you see work from my own group where we're developing methods to explore the internal three-dimensional structure of materials at the nanoscale. And we're hoping to extend this work to the structure of cells. And the fourth leg is the ability to explore and discover properties within the computer. So RPI has one of the world's most powerful computers in an academic setting. We call it the CCNI. Researchers are using this, for example, to look at the atomic properties of doping in semiconductors and the design of molecular motors. So where is this work all going? Well, one very important set of applications is in medicine. For example, work at Rice University in using nanoparticles to target cancerous cells, work to develop much more powerful and sensitive new MRI contrast agents, and work at RPI trying to understand the fundamental ability to manipulate protein function. In the field of energy, we know that the world is going to need many more terawatts of energy supply in future years, and Nanomaterials is providing the ability to develop new ways of storing, transmitting, and generating renewable energy. In the field of the final field is final sort of forward-looking area I want to focus on is in the field of environmental radiation. Work from Rice University here using magnetic nanoparticles to remove heavy metal toxins from water to improve the world's supply of drinkable water. Now, it's important to emphasize that nanotechnology is not just a technology of the future, but of the present. So one major example is in data storage, where extraordinarily sensitive, atomically engineered read-write heads in your hard drive have led to an enormous explosion of the capacity of data storage in our computers. Another field is in catalysis, where these new nanomaterials enable improved control of chemical reactions. And as shown in the top right image at RPI, we're working on ways to improve the surface area of materials to improve catalytic activity. And the sort of perhaps most powerful exemplar of massively parallel manufacturing on very small dimensions is in the microelectronics industry, where ever-shrinking ability to create ever-shrinking device sizes has led to the sort of microelectronics and information revolution. The current device technology can only be shrunk for the next decade or so to certain limits defined by the physical laws of materials or physical laws of matter. So researchers worldwide are looking at new ways to develop nanoelectronic architectures, new way of doing computational switching, using carbon nanotubes, using molecular structures, or in my own work using guided assembly of semiconductor clusters to control the individual passages, individual electrons or magnetic spins. Other applications include new materials for high tension cables. And another field in my group, if you like, we're looking into is the properties of clothing and stain resistant and microbial resistant clothing. And if we really let our imagination run riot and think what might be possible in the future, we might be verging on science fiction, but applications such as space elevators to transport matter into orbit do have champions worldwide, and it's just really exciting to think what the potential future could be. Now, finally, I just want to emphasize that it's very important that scientists, engineers work with social scientists, regulators, the medical field to understand and mitigate possible negative consequences of any new technology. And this is a great focus of the community. It is a great focus of government sort of priorities in this field worldwide. So thank you very much for your attention.
Very good. Very good presentation.